Hello everyone, I am Balachandar and I am going to present about the topic enhancing biocompatibility of titanium alloys in medical applications. As you know, metals used in medical applications must be sufficient, must be able to satisfy a lot of criteria, such as it should be able to withstand wear, corrosion, and it must have really good fatigue strength. Titanium, titanium in this case satisfies a lot of this criteria, and hence it is used in most implants, hip joints, and bone replacements. Titanium has these very good properties when compared to all these all other metals, and so it is used in this medical application. Okay, the most common type of titanium alloy used in medical application is titanium combined with aluminum and vanadium. But since aluminum and vanadium has toxic capabilities, nowadays it is replaced with niobium, aluminum, and zirconium, and molybdenum with a combination of these metals. And titanium, as we discussed before, these are the applications of titanium alloys. They are used in surgical implants and load-bearing support for prosthetic devices, and they are also used in dentistry, like overdentures, crowns, prosthetic components, etc. Okay. There are several factors that determines the biocompatibility of a material. They are determining the toxicity of the elements, corrosion resistance, wear resistance, fatigue resistance, Young's modulus, and osseointegration. Osseointegration is nothing but the integration of the material of the implant with the cells of the bone. These are the common causes of an implant failure. Like discussed before, these are the major contributors that determine the biocompatibility of a material. So, wear resistance, wear or corrosion, and inflammation, that is osseointegration, that also pertains to osseointegration, and fatigue strength, and mismatch in modulus, that is Young's modulus or elastic modulus. Problems caused in these factors leads to a revision in the surgery, and hence they must be attended to. Okay, we'll now look in detail about the factors determining the biocompatibility. Selection of toxic free elements is the most important part in selecting a material for an implant in this application, because when you select a material that is toxic, it tends to be rejected by the body, and hence revision of surgery is unavoidable, as mentioned in this flowchart. And here you can see most of the alloys mentioned in this list has one or two toxic capabilities, and hence the alloys with the least amount of toxic capabilities are only used in this application, for medical application. Okay, coming to corrosion resistance. Corrosion is nothing but destruction of metal when it interacts with the fluids in the environment it is placed in. The debris from the corrosion when planted when planted in the body, the debris from the corrosion will combine with the fluid in the body, and it might travel to other locations and spread the infection. These are all causes, the problems that comes with the corrosion of the implant, and also the corrosion also gives rise to brittleness that leads to failure of the implant as a whole. Okay, how can we reduce this corrosion or improve corrosion resistance in the material? One type of remedy is to coat oxides or nitrates of the respective material onto the surface to provide corrosion resistance. And like we discussed before, toxic elements should be avoided, and the materials can be tested by the help of a Hank solution. The Hank solution is nothing but the solution mimicking the contents of the living body. So these are the contents of a Hank solution. So when a material is tested in the Hank solution, it shows how much resistance to corrosion or wear or any other factor it can withstand. And coming to wear resistance, wear is nothing but similar to corrosion. Wear is nothing but destruction of material, and in that the destruction happens because of friction between the two surfaces. Wear resistance also determines the long life of the material, and this enables the implant to stay inside the living body for a longer period of time. And similar to corrosion, wear causes the smaller particles to fall off and mix with the fluid in the body to spread the infection. How can we rectify this wear in the implant? It can be rectified by changing the alloy constitution with toxic free components and providing a coating of oxide layer, just like the corrosion maintenance part. And we can also add other alloying elements such as molybdenum as a coating layer to reduce the wear. Okay, such as corrosion resistance, wear resistance can be, the implants, the material for the implants can be tested for wear resistance using the Hank solution mentioned before. This is the oxidated surface, and the difference between the oxidated surface and the substance without oxidation, as you can see. Okay, fatigue of a material is caused by repeated loads on a period for a long time. It can cause structural damage of a material, which leads to propagation of cracks, resulting in the complete failure of the material. Wear may be a big contributor to fatigue resistance. Fatigue. This can be resolved by providing a solution similar to that of a wear and corrosion resistance, and just like the remedy of wear resistance, coating elements could be alloying elements could be added to the material to add strength, so as to increase the fatigue resistance, such as cobalt and chromium. This enforces the material and helps the material to withstand fatigue. This is a experimental material that has been coated with a alloying element like alumina to increase the strength. The Young's modulus must be the implant material should be same as that of the bone material, otherwise stress shielding may occur. Stress shielding is nothing but the difference in stress between the material of the implant and the bone. Okay, as defined in this table, a bone has an elastic modulus of 10 to 30, and the titanium alloys, which is the lowest of all of the metals, has an elastic modulus of 65 to 110. This is the effect of low modulus alloy compared with the higher modulus alloy. As you can see, the higher modulus alloy brings about damages to the bone, so it should be avoided. So how to correct the Young's modulus? There are several ways to correct the Young's modulus of the material of bone, such as providing hot rolling, cold rolling, and electroplating and such. And since hot rolling and cold rolling processes are costly, other methods such as powder metallurgy, preparation of the material by powder metallurgy can be used, which naturally reduces the Young's modulus of the material. And material could also be made porous, so that the strength although it reduces the strength, it increases it reduces the Young's modulus. And these pores help in reducing the Young's modulus. Osseointegration of the material. Osseointegration. As I told you before, osseointegration means a cell integration between the material and the bone of the living body. This defines the tendency of an implant to fuse with the bone. Otherwise, it will get rejected, leading to revision in the surgery. The gaps in literature which I found was that the coatings provided for improving the wear and corrosion resistance for certain materials consist of toxic properties, and hence the coating should be revised, and alloying elements used for strengthening the material should also be checked for toxicity. To reduce Young's modulus, materials may be made porous, but since it reduces the strength of the material, alternative methods could be used to keep the strength intact. And some components of titanium alloys emit substances that are toxic to the body, that may be preferred due to their remarkable physical properties, but as such they should be avoided because further processing on those materials adds to the cost. And this is my proposed solution. Instead of choosing alpha alloys, we can choose beta alloys like niobium, zirconium and tin. We are choosing these alloys because zirconium has a very good corrosion resistance, niobium has very good wear resistance, and tin adds strength to the material. And the porosity problem, which reduces the strength of the material, can be rectified by adding polymers by mechanical processes such as pressing. Although the porosity remains in the material, the polymer helps to retain the strength of the material. Instead of providing oxide coatings to the material, nitride coatings could be provided. Nitride coatings are non-toxic and as well as cheap. So these are my solutions provided, obtained from the experiment, and thank you.